I'm Nick, and I am this year's Rover Chief Technical Officer for the Queen's Space Engineering team from Kingston, Canada. Our team is made up of 60 students, split into 4 major subteams: mechanical, electrical, software, and scientific payload. This year we focus on many projects for the design of a mission-ready rover for URC 2020.
The mechanical goals this year were to increase the rover ride height, design non-pneumatic wheels, and optimize the electrical storage box. We redesigned the differential rocker suspension system to increase the ride height, allowing for smooth traversal over rough terrain, which will help during the extreme retrieval task. The team employed finite element analysis and topology optimization techniques to reduce weight while keeping the same structural integrity under maximum loads. Steering away from pneumatic tires, the new 3D printed design went through dozens of iterations to design optimal ABS printed wheel hubs and flexible thermoplastic polyurethane printed tires. The ABS hubs have been printed with 30% infill to optimize the strength to weight ratio, while the outside TPU tires engineered for flexibility, with a tread design that can absorb shocks and grip into rough surfaces. The arm modifications this year include a gripper redesign to better accommodate for the geometry of tools, as well as the addition of the rope pull. Testing and iteration of the gripper is ongoing to optimize for the tasks required in equipment servicing, including pushing buttons and switches, opening latches, and using tools. Based on past performance, the gearing ratio of the arm joints has been re-optimized to ensure adequate strength in all positions and eliminate dead zones. The end effector for the science task was optimized from last year to better incorporate sensors and collect more samples for analysis. The electrical storage box has been modified since last year with the addition of a second shelf to improve cable management and increase cooling to key electrical components.
The focus for the electrical system this year was to overhaul our power distribution network to increase efficiency and reliability. A new dual battery switching system has been designed using high power transistors. This system uses voltage and current monitors to provide diagnostic data, which both aids in determining the optimal point to switch the batteries and in helping to identify system failures during competition. Our new power system has an overall efficiency of 92% compared to the 40% provided by last year's linear regulators. QSET's communication system uses 2.4 GHz antenna, which gives adequate teleoperation distance up to 1 kilometer. Newly added this year is a communication loss behavior safety system that stops the rover in the event of loss of communication during operation, preventing loss of control.
The payload team's focus has been on overhauling of our onboard in situ chemical microreactor for life detection and the creation of a custom onboard embedded sensor system to determine environmental habitability. We chose to focus on 2 main molecules to detect within the soil samples as indicators of extinct or extant life. The Biuret reagent will test for proteins within the soil, which will be indicative of extant life. The potassium dichromate indicator will test for lipids within the soil, which are indicative of extinct life.
The indicator will change color dependent on the presence or absence of chosen biomolecules, which will be analyzed by an onboard spectrometer.
Combined, these results will characterize the soil based on proteins and lipids. Additionally, the pH probe will be used to confirm findings and the suitability of each soil to host life. The microreactor is the housing for the chemical tests. This is fully automated and is built upon last year's design with modifications to minimize sample contamination. The dumping sieve ensures that debris is cleared from the sieve after the necessary particles have traveled in their respective flow paths. These parallel paths ensure that indicators do not interfere with the results of each other. This system is also capable of flushing between samples to again minimize contamination. The habitability of the environment will be characterized by a custom suite of electronic sensors to detect temperature, air, pressure, humidity, UV light, dust, methane, and radiation. The methane sensor will be used in conjunction with the microreactor for additional soil habitability data. These will describe the environment the rover is exposed to, and human suitability can be interpreted from these results.
Establishing reliable testing platforms has been an important goal for this year's software team. This has been accomplished using Gazebo to simulate the robot operating system and a miniature rover for physical system testing. The mini rover has also allowed for testing of the electrical systems for efficiency and heat dissipation. The software team is focused on developing a custom path planning algorithm for the rover object avoidance systems that uses an inertial measurement unit, LiDAR, multiple GPS units, and ultrasonic sensors to autonomously navigate unknown terrain. The success of this algorithm is heavily reliant on accurate GPS coordinates, so an extended Kalman filter has been implemented to improve rover localization. The new search algorithm uses an optimized outside-in radial search and onboard cameras to find AR glyphs. Ultrasonic sensors are placed on the front and sides to reduce blind spots, and LED strips on the chassis are used to indicate autonomous operation and successful object detection.
With a strong focus on reliable operation and competition readiness, QSET is confident that this is our best rover yet.